Guys, this is my Lab 1 video report. To begin with, the purpose of the lab was to record an object moving at the same speed without changing or at constant velocity. Then with this observational model to use Tracker, a computer program to find its position and time and create a position versus time graph. Then by using GlowScript and code given to us by the instructors, we could make a computational model and another computational position versus time graph and compare the two results. The main physics principle used in this was the momentum principle, which in equation form ultimately means that net force equals change in momentum over change in time, which we can then use to find the updated velocity formula. Since this system is at net force of 0, since it's at constant velocity, this equation essentially means that the final velocity equals initial velocity. However, since we don't know either, but we only know the displacement and time, we can calculate average velocity, which would be the same as initial or final, since it will be at a constant velocity. The two models did ended up having different results, but that was due to unaccounted sources of error, but the comparison of the models themselves is intriguing. So the main idea of this was to understand constant velocity, and that when it's at constant velocity, there is a net force of 0 on the system, and the acceleration is 0. This is a little confusing, as if a net force is 0, how do you have motion? Net force doesn't mean that it is all the forces acting on the system, but rather the summation of all of them. So it's just showing that all the forces cancel out. You can still have motion. And acceleration refers to the changing of speed and not to speed itself. So you can have an object going the same speed with a 0 acceleration. I personally chose to use this golf ball model because it just allowed for really simple calculations and really easy way to figure out if there was a difference between the computational and the observed model. As you can see on the left, here's my experiment. I was in my garage with a golf ball that was about 45 grams, and I rolled it across the floor, which was 3.3 meters. I started the initial point of the ball when it had constant velocity, since I was rolling it, so that was about 0.5 meters, and then the final point was right before it hit the end, where it would have stopped and had no velocity, which was 3.25 meters. By using GlowScript to create the computational model almost identical to this observational model, we could create two position versus time graphs and compare them, as I said before. The system in the model would be the golf ball, as it's the one experiencing the force, and the surrounding environment would be the floor and the space around the ball, as they're the one implementing the force. And the ball begins at an initial velocity of 1.4 meters a second. This is also its final and average, as I stated before, and its average velocity is shown being calculated down here. And while there is other forces such as air resistance and friction acting on the system, they're not included in calculations. So with the code itself, there really wasn't much changes from the starter code, aside from the F-net vector being set to 0. The final ball velocity and final ball position had to be changed to match the equations on the left. The initial conditions of the initial velocity, the initial position, and the ball's mass had to be changed to match the observational model. And then the while loop's time interval had to be set to match the time interval of the observational model. So once everything was said and done, the graphs had a fairly similar slope and a fairly similar distance they went. You can obviously see that the observational one is a little less linear, but still follows the linear pattern. The computational model did ended up having a farther displacement, and this could be due to the fact, as I said before, that there's other forces such as air resistance and friction acting on the observed model that weren't in the calculations. These would still have an effect and affect the results, but if they weren't in the calculations, then you wouldn't be able to tell. And then just another source could be the variation, since you do have a computational model that's doing perfect motion every time compared to me throwing a ball on the floor. There's just variation in my throw, or like the ball hitting the tape measure or a small object on the floor. So overall, the purpose of the lab was to capture the object in constant velocity and compare. The observed position versus time graph does show that the object was in constant velocity, and using our computational model, we were able to compare the results and see that the source of error was due to other forces acting on it or variation between the two models. A what-if question is, what if the tracker's axes were changed, and that would just mean that the purple axis was flipped where the x positive was x negative, and that would just lead to a graph on the left here with a negative slope in the fourth quadrant, because you'd still have displacement increasing negatively but time increasing positively. And then could you tell the net force on the observed model? And no, you cannot accurately say the net force on the observed model or give all the forces acting on it. You can only predict and implement them in our calculations to give as accurate results as possible.